Sir, হেৰি আপোনাৰ ভিডিঅ'টো কওঁতে অফো কৰি ল'ব পাৰিব তেতিয়া ইণ্টাৰনেটটো দিগদাৰ নহ'ব চাগে
Okay.
Your entire screen. Click करो.
Share करना है.
go to click करो.
That है. Code.
Okay. और मुझे share करो. बस.
Hide कर लिया.
अगर PowerPoint तो full screen video.
ঠিক আছে স্যার
Hello? আৰম্ভ
হৈছে ভালকে হৈছে পাৰে আপুনি আপোনাৰ পাৰে
আৰম্ভ কৰিব পাৰিব
কৰিব পাৰে হয়
তুমি escape কৰি তোমাৰ ভিডিঅ'টো অফ কৰিব পাৰা যদি লাগে
ভিডিঅ'
তো তোমাৰ ভিডিঅ'টো অফ কৰিব escape কৰা নটিটো
ইয়াতে
ক্লিক কৰা
দুবাৰ
আচ্ছা ভিডিঅ'টো তোমাৰ অফ কৰিব পাৰা যদি অফ লাগে অন লাগিলে অন কৰিব অনে থাকক না দেখা পাব ঠিক আছে এতিয়া
বহুত কিবা কিবি ইমান
পাৰিবি কোনো start কৰি দিম
Good morning to you all.
Yes, sir. So, sir, I think মই start কৰি দিছো অকমান কৈ পেলাই okay. So, welcome you, sir, to this lecture series. Actually, আমি MSc 4th semester এটা এখন special paper আছে আজিকালি ডিপাৰ্টমেন্ট ইলেক্টিভ বুলি কয় ডিপাৰ্টমেন্টাল ইলেক্টিভ তো সেই পেপাৰখনত এটা পৰ্চন হয় যে ম্যাগনেটোস্ফিয়াৰ অফ আৰ্থ এণ্ড আদাৰ প্লেনেটছ সেই পৰ্চন খিনি ছাৰে যিহেতু নিজে এখন কিতাপো লিখিছে স্পেচ প্লাজমাৰ ওপৰত গতিকে ছাৰক অনুৰোধ জনোৱাত ছাৰে মানে ক্লাছ কেইটামান লৈ দিম বুলি কোৱাত মই অত্যন্ত সুখী আৰু ছাৰৰ ওচৰত কৃতজ্ঞ আৰু আমাৰ ছাত্ৰ ছাত্ৰীসকলৰ উদ্দেশ্যে কৈছো ছাৰ ফিজিকেল ৰিচাৰ্চ লেবৰেটৰী প্ৰফেচৰ আছিলে তেওঁ Magnetosphere of Earth and other planets সেইটো এৰিয়া অফ তেওঁ স্পেচিয়েলাইজেশ্যন ৰিচাৰ্চ আৰু ছাৰে আমাৰ ইয়াত আগতেও আচলতে গেষ্ট ভিজিটিং ফেকাল্টি হিচাপে বহুতবোৰ লেকচাৰ দিছে আগৰ ছেমেষ্টাৰবিলাকতো এইবাৰো এনেকৈ ছাৰক লগ পাই আমি তেওঁক আমাৰ বিভাগৰ প্ৰধান আৰু সকলো মানে আমাৰ কলিগসকলৰো হৈ পেলাই তেওঁক আমি ৱেলকাম জনাইছোঁ আৰু ছাৰক আমি ষ্টাৰ্ট মানে ক্লাছটো ষ্টাৰ্ট কৰিবলৈ মই মোৰ ফালৰ পৰা অনুৰোধ জনাইছোঁ ধন্যবাদ ছাৰ আৰম্ভ কৰিব পাৰে
ধন্যবাদ বিনীতা let me start by saying that I'm a frequent visitor I was a frequent visitor to Diffusion University only because of COVID I could not visit Dibrugarh for last 3-4 years, and I'm very happy to get this opportunity to talk to you at least, if not visiting Dibrugarh University, but and would like to start a talk on solar wind interactions with magnetosphere. This is one of my favorite topics, of course, and I have given talk on this topic several times in Diffusion University. However, this time I have 5 lectures with me, and the lectures will be a little bit concise, will not be very elaborate, but anyway, I hope you would be able to understand. Magnetosphere is essentially arises because of the interaction between the solar wind, or nowadays CMEs, with the magnetic field of any planet with intrinsic magnetic field. The main source of energy is the sun. Anything that I am going to talk about, or any kind of processes that I am going to talk about, add energy only with sun. So let me start with one of my favorite slides, where at the top you can see the sun. You know how the sun get or generate energy. If you know how a star is born, then obviously you are aware of the energy that is associated with the formation of the star. And that you know is diffusion. Fusion process, is plasma process, is known quite well. When deuterium and tritium, which are the isotopes of hydrogen, interact, when the temperature is more than 1,000,000 degrees, produces helium and extra energy. But in the sun, this is not deuterium and tritium. It is proton-proton channel. So the proton-proton channel gives rise to the burning of protons, producing helium-4, and this time extra energy plus neutrino. Instead of neutron, you can say neutrino, and neutrino we observe on the ground, and neutrino is the evidence that we have fusion in the sun. But anyway, that is not my kind of topic at the moment. So I would try to proceed further. On your right, you see electromagnetic emission, and on your left, you see mass emissions. So sun produces two very important parts of the emissions. One of them is electromagnetic emission, and in that channel you can see the flare, solar flare is a part of it, and the other is irradiance, and that produces the radiation in a very wide range. And you can, just I can show in a slide, that is the range from gamma rays to radio waves, and in terms of the increasing wavelengths. And these radiations are important. Some of these radiations are very important for the people in the talking of ionosphere or ionization of the atmosphere of any planets. For example, UV rays, X-rays, infrared, and so on and so forth. So these are very important for them, on which we get the ionosphere, ionospheric currents, and so on and so forth, which you are very well aware of. So there are two kinds of emissions, as you know. One of them is the thermal emissions. The other one is non-thermal emissions. And thermal emission depends upon the temperature of the body, which is like a black body radiation. And non-thermal does not depend upon the temperature of the body, but there are other processes like synchrotron radiation, which is given by the electrons relativities electrons going around the magnetic field, and pulsar, and so on and so forth. So I don't dwell with this. This is by the by because I started with the sun. And second part is mass emissions. Mass emissions has two parts. Actually, three parts. One is on the boundary, the solar wind, and the CMEs, and solar flares. These, so to start off with solar wind, we know the solar wind is actually the plasma consisting of electrons and protons flowing out of the surface of the sun and go through the interplanetary medium and meets all the planets with the velocity, which is supersonic velocity. Now, the second one is CMEs. This is coronal mass ejections, which you have already heard, you have already learned, but I'm just giving a short description. The CMEs are coronal mass ejections. A cloud of plasma together goes out to the atmosphere of the sun, or in other words, in interplanetary medium. And the difference is that it has a cloud of plasma with a magnetic field in it. It's not magnetic field tube, but has a magnetic field ropes with it. So there is a mechanism by which it can come out of the sun. The third one is the flares. Flares is actually the kind of explosive phenomena because of some plasma processes, which we know as magnetic field reconnection. It produces also, or it energizes or accelerates the particles and produce the solar energetic particles. Now, I would just like to say a few words of the mechanism that produces these three kind of phenomena. Solar wind is the easiest one. The solar wind, as I said, consists of electrons and protons. Their driving force is the pressure gradient. What is the pressure gradient? How is the pressure gradient produced? If you calculate the pressure on the surface of the sun, which is nkt, and say near the surface of the earth, you can calculate and see that there is a several order of magnitudes of the pressure between the sun surface and that of the surface near the earth. And that produces a gradient, and gradient of pressure is a force, and that force is more than the force exerted by the gravity to pull it back, and therefore these particles come out of the sun and produce a solar wind. And this solar wind is almost there always. There can be variability. That means the solar wind velocity can be high, can be low, can be less. and be low, because depending upon the activity that is there on the sun. So that's the easiest one. The second one is CMEs. I think I should show a picture of CMEs. This picture of CMEs, you can see that it has three parts. One of them, the lowest one that we nearest to the surface of the sun, is the prominence or the filaments. Next is the cavity, and third one is the helmet eruption or helmet streaming, whatever you call it. So these processes essentially tell us that the mechanism by which these emissions, coronal mass ejections, take place is certainly different from that of the solar wind. Here, two processes is important. It is connected with the magnetic field because the prominence is supported by the magnetic field tube on the near the surface of the part. But when there is an activity of the sun, that is the magnetic field either rotating or moving around, then there is a twist in the magnetic field that produces enough energy, and that move this filament out to a region with the magnetic field in it, and there is a magnetic field rope it produces. It is very involved one. I don't want to go into the details of that. And there is a reconnection process by which the foot of the ropes get connected and the ropes together with the plasma goes out. So that's the kind of layman's description of the generation of the CMEs. So that is the mechanism. Therefore, what I'm going to emphasize here is it needs the magnetic field energy, and that magnetic field energy must be converted into plasma energy. So there is a process by which this can happen, and that process is the magnetic field reconnection. So there are two things, important things. One is generation mechanism of magnetic field, and the other one is the reconnection of the magnetic fields. Well, I'm referring this to in the case of sun because similar processes exist also in the magnetosphere of the Earth, which I'll come slowly. Maybe one more picture of the solar flares. Solar flares is the explosion again, plasma explosion, which is associated with the magnetic field lines. Here it is not the magnetic field ropes, but at the magnetic field tubes, which are coming out of the sun because of the fact that they get energy from the surface, from the motions of the magnetic field on the ground of the surface of the sun. They come out, and their magnetic field is then stressed. When it is stressed, it produces a null point. When there is a production null point, and there is a reconnection takes place. As you can see, there is a blue lines and red lines. They are of the magnetic field lines of opposite directions, and they produce a null point on the cross sections and produces explosions, and this explosion produces the jets, which is one that is coming out and the other one that is going down, and that is a signature for the reconnection that takes place. So this is the reconnection processes, which is important for the solar flares. Now this also produces, this processes also accelerates the particles, energetic particles, protons and electrons. They go down and produce X-rays. And X-rays are produced mostly by brimstone in this case. So these are the kind of processes that is associated with the activities of the sun around on the surface. Oh, I think I may mention one or two points about this. This is a sunspot, and sunspot is the sort of source of the all the generation of these mechanisms for CMEs and flares, and therefore there could be a few sentences I talk about the sun. So sunspot. Sunspot is because of the generation of magnetic field in maybe below down in the convection zone, and since it produces a lot of magnetic field, it throws away plasma around, and then there is a magnetic buoyancy takes place, it comes out to the surface. And these activities are not constant. It does not remain all the time on the surface of the sun. It has a kind of cycle, and that cycle, as you know, I am sure all of you know about the solar cycle, these activities, sunspot, and you can see the sunspot numbers going up and down, and then you also see in the picture going up and down and so on and so forth. So this actually leads us to understand the generation of the magnetic field. That is important. Whether the generation of the magnetic field would support the magnetic sunspot cycle, as well as in the case of flip-flop of the magnetic field. So this is one of the most important topic of the solar physicists as well as the art magnetic field people. This you do not need. What I need to show here is that this is this solar wind and CME, and the next picture is magnetospheric effect. That means the production of magnetosphere. So I'll come to that. But before that, I will talk about the generation of magnetic field, process of generation of magnetic field, which would be needed for the magnetic field of the Earth as well as for the sun. Now, what is the origin of the magnetic field of the Earth and other planets? One says it is the active dynamo, is a source of magnetic field. Now the question that one asks always, what is dynamo? And we know what is dynamo in the case of electromagnetic theory or electromagnetism, that if a conductor moves across the magnetic field, produces an EMF, which then generates magnetic field, and that is what is called dynamo. And in the case of plasma, if a cloud of plasma moves across any magnetic field, so plasma is taking the role of the conductor, and then it produces an EMF, which then produces current, which in turn generates magnetic field, and this process is known as dynamo. So this is the lot of work is being done on this dynamo to understand the generation of the magnetic field not only of the Earth, but on the space in the case of Sun and interstellar objects. I give a little bit of history here. Joseph Alarmer, who had first suggested that dynamo should be the processes by which magnetic field of the Sun can generate. However, T.G. Cowling, another famous MHD scientist, magnetohydrodynamic scientist, he gave us a very bad news. What is the bad news? He said no symmetric magnetic field, no axis symmetric magnetic field can be supported by the dynamo, by the process of dynamo that one describes in the plasma or in MSD. So that's a kind of bad news. And therefore, a lot of work was done after that to show how the magnetic field can be generated. Althusser came with a new idea, and he shows that the magnetic field can be generated even by dynamo. T.G. Cowling says that it is not possible to support by dynamo, but that was a second dimension, two-dimensional aspect. But Althusser went one dimension more and generated new setup of equations, and then finally showed that the magnetic field can be generated by the dynamo process. So therefore, we have to understand a little bit of it, and I don't want to go into details of this dynamo theory. That is a huge, vast kind of subject, and a lot of work is being done even today to understand a lot of new things. So to understand this, we need to study the motion of plasma and behavior of the magnetic field. So this, I'll go a little bit of the few equations to show how actually the dynamo produces magnetic field. So I have written that essential to introduce some basic understanding of plasma flow and magnetic field structure. So there are few basic equations that all of us, all of space plasma physicists or the space scientists ought to know as far as the plasma phenomena is concerned is given here. I have not written the first equation. First equation is the continuity equation, which says the mass, which actions is rho d rho dt plus del dot v dot b is equal to gradient of del of b is equal to 0. Now next, this second equation is the equation of motion. Some of you are already very familiar with it, and some may not be very familiar with it. So I will show these equations. But these equations are important to understand certain processes, as I said. So this second equation is nothing but the Newton's second law, motion to acceleration is equal to the force. The rho dv dt gives you the acceleration, and then right hand side you get the all the forces. One is the forces coming out of the pressure, the other one is the Lorentz force. Now this has a long history, or not only history, but it has a kind of processes that got involved in derivation of these equations. It started off with the most important equations of kind kinetic plasma, so kinetic equations like Boltzmann equations or Boltzmann-Vlasov equations. You take the moments and then you derive this type of equation, which is simplest in its form. So what are the approximations that we make in that? We make one simple approximation is that the mean free path is small compared to the dimension of plasma. That is the most important approximation that we make to derive this equation. And even if you do that, you will get a pressure, and that pressure will not be the pressure that I have written. It's not the scalar pressure, but the pressure tensor. Pressure tensor comes there. So it remains complicated there too. And then of course you can get J cross B, which is current and the magnetic field. Now this pressure comes down to the scalar pressure by assuming that the pressure is isotropic. So another assumption has gone that the pressure is isotropic, and therefore we wrote gradient of P like this. So once we have written this, and it will be associated with all the electromagnetic fields like magnetic field and the electric field and the current and so on and so forth, and they would be controlled by the Maxwell's equations. And you have seen I've written two Maxwell's equations there. And third equation is the Ohm's law. The current is equal to the sigma E. Here, since there exists velocity, you have another term 1 by C V cross B exists. That's the Ohm's law. Now, if we make equations, you can get the equation, last equation. Now, what you see that if you make the curl of E, if you take the curl of this equation, you'll get the curl of E there, you'll have curl of J there, and as soon as you get curl of E there, that can be replaced by dB dt, and as soon as you get the curl of B there, and the curl of J there, the curl of B is there. So that would be involve a lot of curls there, and then very easy to look at your vector identity, and then looking at that you can find out, you can derive the last equations. And this equation is that the delta B delta T magnetic field, Xi is diffusion coefficient, del square B, this produces diffusion in the magnetic field, and curl of V cross B is the one which will help you to generate magnetic field. So here you can see the velocity of plasma moves across the magnetic field, produces EMF, and that produces the current, which produces magnetic field. So this can be in this. Here you can see that the equation is nonlinear, because you can have the velocity from the equation 1, which has J and B. If you plot them, if you put them in equation 5, you get the nonlinearity in B, and so therefore equation becomes nonlinear, and these nonlinear equations, nonlinearity gives rise to vortices and other nonlinear interactions which would be associated with the magnetic field. So the magnetic field would be generated. In linear it is simple, but in the nonlinear it goes to nonlinearity eventually and then produces magnetic field. And that magnetic field could be little complex, but still one can get some organized magnetic field. In the case of the art, oh, there is something I must talk before I go to the magnetic field of the art. Here, what I have written that in absence of plasma velocity, Ohm's law is simple. J is equal to sigma E. where the magnetic field is secondary and the primary is electric field and current, and the secondary, and then this can be calculated from the Ampere's law, C curl of B equal 4 pi J. But however, in the case of MST, in the case of plasma, velocity and the magnetic field are the primary, and J and E can be calculated from those two equations, Maxwell's and the Ohm's law. Now from the Ohm's law, you see that E is equal to J by sigma minus V cross B by C. And if sigma is infinite, that be the conductivity is infinite, then the current being finite, the first term can be neglected and E can be given by minus V cross B by C. Now if that happens, then this is, we call it hydromagnetics. What happens then? Then that leads to a very important plasma processes called frozen in field condition. In fact, when that happens, if the plasma flow with the magnetic field, one can find out the flux of the magnetic field at one point, and then it moves to the other point, it can find out the flux of the magnetic field at the other point. If E is equal to minus V cross B by C, then it is so seen that these two fluxes are the same. Their magnetic intensity is the same. That essentially means that the magnetic field is frozen in plasma. As the plasma moves, magnetic field moves along with it, and that's the kind of the processes that the Alvin, that one of the processes for which Alvin got the Nobel Prize in plasma physics. So this is an important concept in the plasmas in space, which we ought to know. We are spending this first lecture on this, and this we should remember that the magnetic field is frozen in plasma. When there is a conductivity which is infinite. If it is not, then it is not. So I've written that. So for now, large sigma, J and sigma can be neglected. Electric field is driven by the velocity and the magnetic field. Now if you go back to the earlier equation, that is on the right hand side of equation 5, you have two terms, and we can compare the first term with the second term only by changing delta as kind of length, inverse of length. So that if you do that, then you can get a parameter called Rm. As you can see, Vb by L divided by xi b by L square and Vl by xi. Xi is a very small quantity, and V is velocity, and L is the dimension of the changes in the magnetic field. So the Rm is called the Reynolds number, and this Reynolds number can be very large if the conductivity is infinite, or if the resistivity is small, if the diffusion is small. So if that is large, then obviously E can be given by V cross B by C, and that will give rise to the case when the magnetic field is frozen in plasma. So when the Reynolds number is very large, magnetic field is frozen in plasmas. So this is a concept. I've given two things in this case. One is the frozen in field concept, frozen in field, and the other one which is associated with the Reynolds number. So then therefore I can go to the next page. If you have some question, you can stop me and ask. Or maybe end of this lecture. Now, in the case of the art, I have not shown how things have happened. In the case of the art, because of the rotation or because of the plasma, hot plasma at the core of the magnetic core of the art, which is the inner core, and because of which the magnetic field is produced. The plasma is moving across a magnetic field. Of course, you need a seed magnetic field to start with. So then the rotation of the plasma will give rise to magnetic field. And as I have said, that is not a very simple process. Indeed, it can go to the nonlinear level, and when it goes to nonlinear level, it can give rise to vortices and a lot of other things. So here in the magnetic field of the art, it goes through two stages. First, it produces the toroidal magnetic field, and then because of the Coriolis force, the toroidal magnetic field comes out of the surface and then produces the poloidal magnetic field, which we see. And look at this picture. This is a kind of computer simulation of the magnetic field generation, and you can see that even with unorganized thing, you can get some organized magnetic field. One, it looks like a dipole magnetic field, and therefore we see the dipole magnetic field in the case of the art. And then you see the blue ones, the magnetic field is coming in, the yellow type 1 magnetic field goes out. So they make a loop, and then you can see the magnetic field picture of the art, which looks like the dipole magnetic field. And therefore, that's why I have spent so much of time in doing the understanding the generation of the magnetic field of the art, and by which you see the magnetic field of the art can be generated by the dynamo. That is an important aspect of my presentation, that the dynamo is the source, is the mechanism by which magnetic field of the art is generated. Now, as I said, that is a complex process, and one always asks, the magnetic field of the art gets kind of flip-flopped in the history of the magnetic field of the art. One sees that the magnetic field gets flip-flopped. That means it goes toward the north pole, goes toward the south pole goes toward the north. So there is a flip-flop can happen. Now, not can happen, it has happened in the history, in the observations, it is seen. Now, the question that one asks is, the dynamo is capable of answering that question, whether it is really giving rise to flip-flop mechanism of the magnetic field. Or in the case of the sun, is it possible to produce 11-year cycle of sunspot? That means 11th year of cycle of magnetic field generation. So then there are a lot of questions people ask, but again the LSSS and other people had shown a system of magnetic field, a system of equations which remains invariant if you change the magnetic field. That means even if you change the magnetic field, the dynamo action takes place and the magnetic field can be generated. That is the indirect way of suggesting that it can support the flip-flop, or it can support the magnetic field cycle that is associated with sunspot. Oh, this is the reversal that the flip-flop I have seen. This is the kind of observation that the geologists had. As I written that the Earth's magnetic field is known to have reversed its polarity in the past. That is, the magnetic field has flipped to flow from north to south. These reversals are not periodic, and episodes of constant polarity vary greatly in length. History of reversals of the Earth's magnetic field is very well known for the past 200 million years. What they call magnetostratigraphy, that is the way of tracing the magnetic field in the clays or in the soils or in the rocks, are being coded, and they have seen the reversal in the sequence of rocks. There are different rocks. If they go toward inside the art from the mantle, and they can see different types of rocks, and in all rocks had some magnetic field signature in it, and those magnetic field signature tells that in times the magnetic field got changed from north to south or south to north. And this the fingerprint can be used to date rocks in correlating different rock sequences. Or this can be used as a barcode. Nowadays, everything goes with the barcode, so this can be used as a barcode for the signature of changes in the magnetic field. Oh. Now, before I actually go to the interaction between the magnetic field and the solar wind or CMEs, I have few words to talk about the generation, the dipole description of the magnetic field. And as I have seen that the phi is the potential, and it consists of two sources. One is phi I, which is the potential due to the internal origin, and phi is the external origin. Now, you may ask what is the external origin and what is the internal origin. Internal origin, we have just now talked so much of it, that it is the plasma flow or the fluid motion in the core, inside the core of the Earth, which interacting with the magnetic field or a seed magnetic field produces a magnetic field, and that is associated with the potential that we call internal origin. And that is the main part of the magnetic field that is generated in the case of magnetic field of the Earth. The second part is phi E. Phi is the external source, and you know much better than me that external source of the magnetic field or magnetic potential is the ionospheric current. And you know much more about the ionospheric current than me, and then that is what is responsible for the IE. Where I can add something more, I can add some magnetic field associated with the magnetosphere, which is associated with the ring current, in the magnetosphere, and ring current produces magnetic field on the ground, and that goes also to the description of the magnetic field of the Earth. However, we assume that the external contribution is negligible, so the main potential field is due to the internal magnetic field, which can be described as a dipole. If you describe it as a dipole, phi is equal to phi I, and that is equal to m dot grade 1 by r. Well, for that you have to go to the your lesson on electromagnetism, where magnetic m is the magnetic moment and r is the distance from it in the direction of r. So this can be I can give rise to m by how it can be done. Well, you can m dot gradient of 1 by r. Gradient of 1 by r is 1 by minus 1 by r square, and in the direction of r prime or r hat, m and r hat, there is an angle between r and m. And that angle is, in the case of the Earth, is the co-latitude, and m dot r then would be m cos theta, m or cos theta, cos mod theta is the language, then that can give rise to the phi m by r square cosine theta. Theta is the co-latitude, because m is in the direction towards the north, and r is any direction. So r and m makes an angle theta, and m dot r gives you cos theta, and therefore m by r square cos theta. Anyway, if I had a blackboard here, I could have shown how it is done. But anyway, you can derive it. And magnetic field or any electric field, whatever, if you know the potential, you can find out the magnetic field or electric field. Say electric field is equal to minus gradient of phi. Here m v is equal to minus gradient of phi, which gives the two components Vr and V theta minus del phi delta r, and that gives rise 2 by m r cube cosine theta. And B theta is minus 1 by r d phi d theta, and that gives you m by r cube sine theta. What is theta here? Theta is the co-latitude. Now if you, and I do not write b phi because in the azimuthal angle, I assume that the magnetic field is sort of uniform all around, so there is no gradient in the potential, so therefore b phi is not there. So B theta is a magnetic field associated with the dipole, and you can find out the total magnetic field. Total magnetic field is B r square plus B theta square to the power half, and if you put them together, they're like this. Then you can simplify, and that simplification is given as m by r cube 3 cosine square theta to the power half. But if you want to express in terms of not co-latitude but latitude, simply you change lambda is phi by 2 minus theta, whereas lambda is latitude, and you can get this expression, and b is equal to m by r cube 1 plus 3 sine square lambda. So one thing is clear, that what if you have a dipole magnetic field, then the b varies as 1 by r cube. If you go in the direction of r, then b varies as 1 by r cube. And of course, the theta variation is given by 1 plus 3 cos square theta, or 1 by 1 plus 3 sin square lambda. So these are the dependence of the magnetic field on the r and theta. R is the distance in the radiation in the radius direction, radial directions, and theta is in the directions of the uh, latitude or co-latitude. So this is a kind of magnetic field that you can get in the case of this. Oh, now the other point which I am giving here is the equation of field lines. It is important to write down, obtain the equation, knowing the magnetic field kind of expression, configuration, you can find out the equation of magnetic field lines. Why? Because if dl is an element along the directions of the magnetic field line, and B is the magnetic field at that point, then the directions of the magnetic field and the field line direction does not change, is the same. And therefore, B cross dl is equal to 0. And dl can be written as dx dy dz, B can be written as dx dy dz, and you can find out cross product of bx by bz and dx dy dz, and you can find out a simple relation, bx by dx, by dy is equal to bz by dz. So that is the equation of the magnetic field line. Now we can obtain in terms of the polar coordinate, because we have obtained the magnetic field in the dipole in terms of polar coordinate. So that can be obtained in terms of polar coordinate too, and therefore you see that Br by dr and b theta by r d theta, and here we write term b phi r sin theta d phi, but d phi does not exist, and because b phi is 0, and therefore we get only dr by br r d3 by b theta, and if simple kind of algebra, if you do it, then this is what you get. You know the br by d theta you can obtain from the expression for br and b theta. Put them together, you get r equal to integration of 2 cos theta sin theta plus a constant c, which can be written as 2 log of sin theta plus c, and you can find out constant by saying that r equal to r0. R0 is the distance along the equatorial region, along the direction which is the equatorial plane. So you can find out r equal to r0 when theta is equal to pi by 2. So then you obtain r0, and then the equation becomes r equal to r0 sin square theta. You divide it by r0 radius of the arc, so you get r L sin square theta. What is L? L is the r0, that the distance of the magnetic field in the radial direction in the equatorial plane, and r0 is the radius of the arc, and that gives you the L. So L determines the distance from the distance of magnetic field in the equatorial plane from the center of the arc. So R is L sin square theta. So R is measured in the radius of the arc, not in kilometers, not in centimeters, but in terms of radius of the arc, and therefore R is equal to L sin square theta. You can make it all R equal to L cos square lambda if you want to express in terms of the latitude instead of co-latitude. So then there is an important aspect here, or definition here. His definition is invariant latitude. Suppose you are in the equatorial plane of the Earth at a distance, say L, or some distance, and something goes along the directions of the magnetic field, and you want to find out at what latitude it is going to end up, or what latitude it is going to land. So that can be obtained simply by knowing this value of L. How? This is a simple derivation, because when you land in the Earth's surface, then R becomes R0. When R becomes R0, then left hand side it becomes 1. And say that lambda becomes some specific lambda, capital lambda. So put them there. You find out that cos square lambda is 1 by L. So if you know L, you can find out lambda. That means if you are at a distance of L, and if you are walking along the magnetic field lines, you are going to end up at a latitude which will be determined by 1 by L to the power half. And that is given there, and that gives you lambda to be 60 degree. So your lambda is at the 60 degree. So anyway, if something happens at the equatorial distance, or if something happens at L values, if you know the L values, then you can certainly find out the latitude at which it is going to end up, which is going to interact. And that is called invariant latitude. And that is very important when you describe some of the processes that is happening in the magnetosphere. Suppose you have a lot of energetic particles at a value L equal to 6, for example. Then those electrons or protons which are very energetic could move along the directions of the magnetic field, will end up at lambda is equal to 60 degrees. So that area of the Earth is going to be affected by those. So that's an important aspect also of the magnetic field approximation of the dipole. And therefore we started with the sun. We talked about the generation mechanisms of 3 things: solar wind, Siamese, and solar flares. And we found that we have to know the generation of magnetic field, and as well as the reconnection process, to understand the generation mechanism of the solar flares and Siamese. And then we got down to the generation of the magnetic field and how the dynamo processes is the process which produces a magnetic field. We had come down to the Earth, and we had shown that the same dynamo also exists in the interior of the Earth, which produces a magnetic field. And then a complex picture of magnetic field is shown, which is obtained by the computer analysis, computer simulation rather than analysis. And then even with all these irregularities, we found out some regularity, and that is a kind of dipole magnetic field. And then we described the emitted dipole magnetic field in case of simple quantity is the distance from the sun, is the distance from the center of the earth and the latitude. Then we describe the invariant latitude. So these are the total aspect, that total summary of what we have done today, and these are important aspects of what we are going to talk about next time. Maybe I have crossed, I think, my time. Anyway, next time we'll talk about the solar wind or semi interaction with the planets. So maybe it would be nice to start from the beginning of the magnetospheric processes next time. I'll stop it here. And if you have any question, you can ask me. Let me see how I can get back.
Thank you, sir. Students, কিবা question থাকিলে সোধা। Sir, আপুনি structure to পঢ়াব চাগে নহয় জানো magnetosphere? Magnetosphere structure, magnetosphere, earth magnetosphere structure.
This is the introduction.
Introduction only, yes. Okay. কিবা question আছে যদি সোধা তোমালোকে ছাৰক।
My question? But anyway, some people are these are some well known to a lot of people, so maybe there may not be any question today. Quick. কিবা কৈছা?
Sir, more second connection.
কোনো question? আপোনাৰ কিবা এটা সুধিবলৈ লৈছে চাগে, সোধা কিবা আছে যদি। নাই যদি আমি stop কৰিম।
Next time there will be more questions.
Hope so.
আজি বেছি question নাই কাৰণ এইবিলাক সবে জানে চাগে। নাইবা অলপ different.
Actually, CMEs and sunspot or solar cycle, these things, মই যিখিনি পেপাৰ লোৱা ষ্টুডেন্টছ আছে কিন্তু সবকে নাই কোৱা আচলতে।
সবকে নাই কোৱা মানে যিকেইজন তোমাৰ ষ্টুডেন্ট তাহাঁতকতো কৈছা। ঠিক আছে, জেনাৰেশ্যন মেকানিজম বিলাক যদি লাগে মই পিছত
থাকে, পৰহিলৈ থাকিব। পৰহিলৈ আপোনাৰ আকৌ থাকিব ক্লাছ 10:30।
পৰহি কেইটা বজাত? 10:30
to 11। হয় হয় 10:30 to 11:30 হয়।
ওকে, ঠিক আছে তেতিয়া আজি থওঁ তেতিয়াহ'লে। ওকে।